Have you ever stopped to think that the universe might actually be dying? Not slowly, like a candle burning out, but in a violent, accelerating expansion that no one can explain. There's an invisible force pushing galaxies apart, stretching the fabric of the cosmos faster and faster. And this force has a name: dark energy. It makes up over 70% of everything that exists, yet we barely know what it is. All we know is that it's winning. And if it keeps growing, one day, not even light will be able to reach another galaxy. The universe will become a dark, cold, and lonely place. The most disconcerting part about dark matter is that it's everywhere, except where we can see it. It doesn't shine, it doesn't emit light, it doesn't reflect anything. If you were standing in front of a block of dark matter right now, you wouldn't see anything at all, like looking straight into the invisible. And yet it would be there, with mass, with gravity, with presence. It's like feeling the weight of a ghost. It's all around you right now. Yes, right here on Earth. In your bedroom. In the space between planets, between stars, between galaxies. Dark matter permeates the universe like an invisible cosmic web. About 85% of all mass in the universe is made up of it. And yet, we've yet to capture a single particle directly. Want to know where it concentrates? On large scales. Dark matter forms gravitational halos around galaxies. It acts like an invisible glue, holding galactic clusters together, and without it, these structures would simply fall apart under the speed of their rotations. That's a fact. It's not inside the stars, but around them. It's not part of the planets, but surrounds them. It's like a field, dense where gravity is strongest, thin in the void between galaxies. Now comes the coldest mystery in the universe. What is the temperature of dark matter? The short answer? No one knows. But most models suggest that it is free, literally, so cold that it moves slowly, hence the most common name in studies is cold dark matter, or cold dark matter, CDM. This is important because if it were hot and moving fast, it would not have grouped into structures like galaxies. It would be too agitated, too spread out. Its coldness is what allows the formation of the cosmos as we know it. As for color, dark matter has no color. And it's not because it's black. Black still reflects something, still absorbs. Dark matter is transparent, invisible, untouchable. Lights pass through it, as if there was nothing there. It's as if it were in another dimension, interacting with our world only through gravity. Not even the best telescopes can detect it directly. We only see what it does, not what it is. And the craziest part, it doesn't interact with ordinary matter, at least not like any particle we know. It doesn't emit radiation, it doesn't collide with atoms, it doesn't heat up, it doesn't cool down, it doesn't vibrate. It's as if it exists behind an opaque mirror, shaping the universe in secret. But what about density? Dark matter is extremely dispersed on a small scale. Inside your house, for example, there may be millions of dark matter particles passing through you right now per second, but since they don't collide with anything, they pass straight through. However, in large cosmic volumes, this rarefied presence adds up to a massive force. It's as if the universe were a model made of light and gas, mounted on an invisible structure of dark matter. Some scientists are trying to imagine what it would be like if we could see dark matter. It would be like seeing invisible clouds with colossal shapes, immense webs crossing the cosmos, connecting galaxies like wires in a giant electrical grid. A universe within the universe, only made of silence and shadow, and that's why she's so fascinating. Because even though she's invisible, she's there, everywhere. It is the skeleton of the universe, supporting everything we know, but never showing itself. Dark matter is not just a scientific mystery, it is a presence, a force that shapes entire galaxies, passes through our bodies and influences the fate of the cosmos, all without emitting a single beam of light. Now that we know that dark energy exists and that it dominates the universe, the question that keeps cosmologists awake at night comes: how does it all end? Because if the force driving the expansion of space is not only active, but accelerating, then we are watching the beginning of the end. just in slow motion. And here comes the most fascinating and disturbing scenarios in modern cosmology. Dark energy, depending on how it behaves over time, could lead the universe to completely different endings. Let's explore the main ones. And brace yourself, because none of them are exactly comforting. A big freeze is the most accepted future among scientists today. If dark energy continues to act in the way we see it now, the universe will continue to expand forever. The galaxies will move so far away from each other that, in time, none will be visible from the other's point of view. The space will become a big, dark, and silent desert. The stars will die. First the small ones, then the giant ones. Planets will wander in the sunless cold, and even black holes will slowly evaporate through a process known as Hawking radiation. After trillions and trillions of years, the universe will be an empty icy sea, with temperatures close to absolute zero. Nothing will shine. Nothing will change. An eternal cosmic cemetery. O Big Ripus, one of the most dramatic and frightening endings. Imagine that dark energy is not stable, that it is increasing over time. In this scenario, the expansion of the universe doesn't just keep accelerating, it accelerates more and more, faster. And there comes a point where this acceleration becomes catastrophic. First, entire galaxies would be torn apart. Then, solar systems. Planets would be ripped from their orbits. But it didn't stop there. Stars would be destroyed. Atoms would be torn apart. Even subatomic particles would be torn apart, as if the very fabric of space-time were ripped in half. Hence the name, the Big Rip. An end that happens from the inside out, as if the universe were silently exploding. The question is, for this to happen, dark energy would have to get denser over time, which so far we haven't observed. But the universe has surprised us before. Now let's turn the tables on the big crunch. Suppose dark energy is temporary, a phase that could change or even disappear. If that happens, gravity could take over again, and then, instead of expanding, the universe would start to shrink. The galaxies would stop moving away and start moving closer together. All matter, all energy, everything that exists, would be pulled back to a single point. A cosmic collapse. The universe would end where it began, in a new reverse Big Bang, a big crunch. And who knows? Perhaps this collapse would give rise to a new universe, restarting the cycle. It's poetic. But the current data doesn't support this scenario. So far, everything indicates that dark energy isn't going away. On the contrary, it seems increasingly stable. Oh, Big Void. It's one of the saddest scenarios, and often confused with the Big Freeze, but it's even emptier. Here, the universe expands so much that the very fabric of space begins to become unstable. Galaxies not only move apart, but they stop forming stars, lose their matter, and everything enters a slow thermodynamic collapse. There is no rip, no explosion, no drama. Just silence. Pure entropy. A death by exhaustion. The universe becomes an endless sea of solitary photons, without interaction, without meaning, without time, and perhaps without observers. It is the end of complexity. Cutting-edge cosmology is increasingly open to ideas that once seemed like fiction. Some models suggest that the universe doesn't end, it just changes. Based on quantum gravity, some scientists speculate that the collapse of the universe in a big crunch could trigger a big bounce, a new universe rising from the ashes of the previous one, like a cosmic phoenix. Other theorists talk about an inflationary multiverse, where our universe would be just one bubble among infinite ones, and dark energy would be a byproduct of our cosmic neighborhood. In this case, the end may mean nothing, just the transition to another universe with different laws. And there are still those who talk about daughter universes created by black holes. Every time a black hole forms, a new universe could emerge on the other side. If this is true, the end of our universe would be the birth of others, an infinite tree of realities. Despite being invisible, dark matter may have a microscopic structure as complex as that of ordinary matter. Scientists are hunting for hypothetical particles that could make up this cosmic enigma. One of the most famous candidates is WIMPs, weakly interacting massive particles. They would have mass but would interact very little with ordinary matter, which would explain why we never see them directly. Another bet is axions, extremely light and low-energy particles, almost like cosmic ghosts, capable of crossing entire galaxies without leaving a trace. There are also sterile neutrinos, which do not interact even with known forces, except gravity. And in bolder theories, some suggest that primordial black holes, formed in the first milliseconds after the Big Bang, may be the real ones responsible for the gravitational effect that we attribute to dark matter. The problem? None of these candidates have been detected so far. We are literally groping in the dark. The hunt for dark matter is taking place on three main fronts. The first is direct detectors, buried kilometers underground, shielded from cosmic noise. They try to detect a collision between a dark matter particle and a regular atom. Projects like LWEX, Xenon 1T, and PandaX are examples of this approach. The second line of attack is indirect. We observe space in search of secondary signals, like gamma rays, neutrinos, or antimatter, that could be produced when dark matter particles annihilate each other. The third front is particle accelerators, like the LHC, where we try to create dark matter from very high-energy collisions. In each case, the result has been the same: silence. No direct evidence, but each failure helps us narrow the search field and rule out hypotheses. There is a school of thought that challenges all of this. What if dark matter is just a misinterpretation? That's the idea behind modified gravity theories. Rather than adding invisible matter, these hypotheses propose that the laws of gravity as we know them simply don't work the same way on large scales. The best known is the MOND, modified Newtonian dynamics theory, which alters the formula for gravity in very low acceleration environments, such as the edges of galaxies. Interestingly, it explains some observations that dark matter also explains, but it fails on others. The biggest challenge with these alternative theories is that they don't hold up well when tested on larger scales, such as galaxy clusters or the cosmic microwave background. Still, the existence of these ideas shows how far we are from understanding the universe completely. If dark matter is 5 times more abundant than ordinary matter, why do we assume it is inert? This question has led some physicists to imagine the unthinkable. What if there are complex structures based on dark matter? Entire civilizations, perhaps, living in a kind of parallel reality that interacts with ours only through gravity. These ideas border on science fiction, but they gain traction precisely because of the void that science has yet to fill. The concept of a dark biosphere, with planets and life forms made of dark matter, is extremely speculative, but mathematically possible. The big barrier would be the absence of electromagnetic interaction. That is, no light, no conventional chemistry, no communication. It would be a completely alien type of existence. But if there is one thing the universe has taught us, it is that it does not care what we find plausible. These ideas may seem far-fetched or crazy now, but that was the case with the idea of dark matter itself. Time and data will decide what remains standing. For decades, we treated the expansion of the universe as something simple, a continuous accelerating motion, driven by an invisible force called dark energy. But what if we're looking at all this the wrong way? There is a possibility that is beginning to gain traction among theoretical physicists, that the universe isn't expanding in space, but rather that the person himself time is changing pace. It sounds absurd, but think about it. All of our observations of expansion come from the light of distant galaxies. This light reaches us more stretched, as if the universe were moving away. But this stretching may not be caused by movement. It may be caused by a fundamental change in the fabric of time itself. If time slows down imperceptibly for us, who are within it, everything around us seems normal. But the light coming from the past carries a different signature. It reveals that something is slowing down, or that something is changing in another layer of reality. Some theorists propose that what we call dark energy may actually be a reflection of time no longer flowing linearly, as if the universe were entering a new state, not spatial, but temporal. This kind of idea is still on the edge of scientific speculation, but it has a powerful advantage. It would explain why we have never been able to detect dark energy particles. Maybe because they do not exist as particles. Perhaps we are feeling the effect of something even more fundamental, a mutation in the very fabric of time. If this is true, then the end of the universe may not be an explosion, a freeze, or a collapse. It might be something stranger than all this. Time can simply stop existing, not with an explosion, not with an event, but with such absolute silence that there would be no before or after. Now we're going to get into even stranger territory. What if dark matter is just the tip of the iceberg? Because there is a disturbing hypothesis being discussed behind the scenes of cosmology, that what we call dark matter may not even be a substance at all, but rather a symptom of our misunderstanding of the laws of gravity. That's right. There's a school of thought that suggests that gravity as we know it might not work the same way on cosmic scales. This idea is called modified gravity, and there are several models. One of the best known is the Mond theory, modified Newtonian dynamics, which attempts to explain anomalies in the rotations of galaxies without needing to invoke dark matter. According to this theory, what we're seeing in galaxies isn't the effect of an invisible mass, but a flaw in Newton's equations. When applied to very large distances, it's as if gravity behaves one way here on Earth and completely differently at the far ends of the universe. A bit like discovering that water boils at 100 degrees only in your town, and it doesn't stop there. There are even bolder versions like the string theory and the idea that we live in a universe with more dimensions than we can perceive. In this scenario, gravity would leak into these other dimensions, weakening its action on our visible world, and what we interpret as dark matter would be just the shadow of something bigger, operating in a universe parallel to ours, but which still leaves footprints here. There is also the possibility of scalar fields, particles that do not have mass like the ones we know, but that can fill space with mysterious properties, functioning as a diffuse force, like an invisible field that alters the behavior of the surrounding matter. If this exists, we're not just talking about particles we can't see. We are talking about physics that we have not even begun to understand yet, and this is perhaps the most uncomfortable part of all. Dark matter may not even exist. It may be that the universe is playing tricks on us, and that our current tools are incapable of revealing the true workings behind the cosmos. But until an alternative theory can explain what dark matter explains today, galaxy formation, mass distribution, gravitational lensing, the structure of the universe, it remains the best hypothesis, not because it's comfortable, but because, strange as it may seem, it works. The truth is, dark matter remains one of the greatest mysteries in the universe. We know it's there, shaping galaxies, influencing cosmic fate, but we still can't see it, touch it, or fully understand what it is. It could be a new particle, a flaw in our physics, or something beyond imagination. What matters is, it's steering the story of the universe, and the end of that story might depend entirely on it. In the end, dark matter is a reminder that the universe still holds countless secrets, and maybe the most important ones are still invisible. If you enjoyed this dive into the unknown, hit the like button, share it with your fellow space lovers, and subscribe to the channel. There's way more mystery on the way. See you next time.